Okay, we start up again. Continuing with system analysis, system simulation. The way we have to couple, the different elements within a system to each other is physical laws. So physical laws, now we are talking Newton's second law of motion, gravitation, Bernoulli, a law. That is something you can't really develop, you can't prove it. You just say this is Mother Nature and we believe this law until somebody proves it wrong. You can't develop Newton's second law of motion. You just state this is the case. That's a physical law. Also, we have something called constitutive equations. Constitutive equations, they are equations trying to give a simple, easy model of Mother Nature. They're not physical laws. We know they are more or less wrong, but they are simple, easy to handle. So physical laws, say the mass times acceleration is the sum of the forces. Constitutive equations, ideal gas law, for instance. We have Kirchhoff's laws, Ohm's law, and so on. Things like that. Also, we have another type of problems. We have kinematic. Say relations, correlations, equations. This will be kind of physical limitations, connections. For instance, you have a wheel here rotating at a certain angular speed, and then here we have a rod into a mass that can slide back and forth. So here you will go from rotational motion into the motion back and forth. This coupling, this connection, will be given by some kinematic equations, some constraints, some description there, which is sort of absolute in such a slide, for instance. So these are the tools we are going to use to couple all our problems or our different element of the problem together in one single big problem. What we end up is a set of ordinary differential equations. Ordinary differential equations, for short ODEs. Ordinary differential equation, not partial differential equation. No curl derivative here, only normal derivatives. And some definitions here. We have the order. An order of one single ordinary differential equation. What order are we talking about? That is the highest derivative. In one ODE. Typically in math, you start first by first order differential equations, then you go to second order, and then you stop. So third, fourth, and so on. The math, they don't have time to do that, but you get the idea at least. What about when you have a whole bunch of these coupled together? order of a system, and now we are talking a system of ordinary differential equations, a set of them, then we have to take the sum of the orders that enters into the system. So as an example, we have say x double derivative, here a dot meaning time derivative. So this is a double time derivative plus, and then I have alpha x dot equals y, and here I have y dot plus beta y equals a function of time minus x. So clearly they are coupled. You find the x's and the y's mixed in these two equations. So that's a set of two coupled ordinary differential equations. The first one, that is a second order. The last one, that's just a first order equation. So the order for this system here, both of them, that is a third order system. Third order system. Third order. We will not handle systems like this. We don't like it. What we are seeking is a set of only first order equations. So everything here is okay except this double derivative. We hate double derivatives. Get rid of them. How to get rid of it? Well, we do the general trick. We baptize a new variable, u. He will be x dot. Then the second equation will now be the first one here, but written with u dot plus alpha x dot equals y. The last one, well, you can keep it as it is, no problem with him, plus beta y equals f of t minus x. Now you have three first order differential equations. You can always do this, regardless how complex the equations are, how many dots you have here, doesn't matter. You can always rewrite it as a set of first order equations. That's possible. Of course, you can go the other way around. It should be possible with these two equations to rewrite it as one single third order equation, or with x or y if you want to. Yes, you can do some algebra here. You could eliminate y, setting these two in here and taking the time derivative of this equation. You will end up with one equation with x only. Yes, that's possible. Then you will have one single third order equation. But don't do it. No. This is what we are going to do. So here in this problem, x and y, and now also u, is what we call the dependent variables. So, or the state variables. Take it from, it should be here somewhere. State variables. State variables, also the dependent variables. Will now be x, y, and u. So we have three of them, meaning you need three first order equations to describe the system. and then these three should then describe the system unique. So you know these three, you know everything about the system. These are the dependent variables. What is the independent variables? Anybody knows? A variable that doesn't depend on anything else. The independent variable for this problem here, that's time. That's t. Remember, you have the time derivative for the basic equations. We are now seeking the solution. The solution might look something like this: x of t, y of t, u of t. These three functions, they will be our solution. This is the answer. That's what we are seeking. No questions so far? Please just interrupt me anytime you have a question. That's okay. Yep.
The second equal should be u plus.
This one?
Yeah.
Yeah, because I just baptize u as x derivative. So u dot will now be x double dot.
Yeah, but then alpha and then x dot.
Yeah, so here you could have used u, or you can use x dot. We still have the x anyway, so it will be the same system. It's just a matter of how you like to program it. So you could use u, or you could use x dot if you like. You see, for this problem here now, it's better, as you say, to have u instead of x dot, because I had an x dot already. So now it's simpler to program. The way we want it actually is here. I want this one on the form x dot equal, y dot equal, u dot equal. That's the way I want it. Then it's easy to program. And as you suggest, use u here instead of x dot, much easier. Good. Other questions? Okay. To be able to solve this problem, we need initial conditions. That means we need to know our state variables, all of them, at a certain time, typically t equals 0. We need to know everything about our system at a certain time. Else we can't predict the future. So initial conditions, that will now typically be x of 0, y of 0, u of 0. We need those. They should then define a unique state of our system. More about ODEs. We talk about linear versus nonlinear. And a linear ODE versus a nonlinear ODE. What about this set we have here now? Those three equations, they should be linear equations. We don't have anything squared or cosine or x or something nasty in here. So this will be a linear set of equations. And what's nice with linear, we can solve them typically or normally. Analytical solution is possible. Also, it's possible if you have one solution and then you have another solution, then you can combine them to make solution number 3. You can superimpose solutions, as we call it. So here, superposition is possible. But as I said earlier, our problems, they are in general not going to be linear. They are going to be nonlinear. And with nonlinear ODEs, we have to simulate. So, for example, we have something like this, x double plus cosine omega times t, cosine omega t or sine omega t for a harmonic motion. That is something that occurs frequently. Multiplied with x dot multiplied with time to the power of 3 equals time times exponential minus alpha t. This is a linear partial differential equation. It's actually linear. Because the dependent variable here, it's x. And time, well, he's an independent variable, so he can be whatever he wants. He doesn't destroy anything with the linear versus nonlinear. So we have x dot and I have x double dot, no problem. If I have this one, x double square, nonlinear. That's something else. Now we have a nonlinear equation. Or here, for instance, I have y multiplied with x, nonlinear. Linear. Yeah, and finally, when you have the time is given, it appears explicitly into the equation, like it does with this one. Actually, the time enters several places. For this set, we have this unknown function f of t. We don't know what it is. It can be anything. Whether it's a linear function or non-linear function of t doesn't matter. It doesn't change the order of the system, doesn't change whether the system itself is linear or non-linear. But time here may enter explicitly. When that happens, when you have time explicit, you call them non-autonomous. Non-autonom. Let's see, autonom and non-autonom. Here you have time explicit, like cosine omega t, for instance, and here not time explicit anywhere in your equations. So if this f of t, if he is a constant or not present, is just 0, then this set will be an autonom system, no time. If time is here, some expression including time, it will be autonomous system. Okay, that was just some definitions, so you know a little bit what we're talking about. Whether it's autonom or non-autonom, we don't really care. It's no problem for us anyway. If it's a linear system, well, that's cute, but we don't care. We're going to simulate it anyway. Sometimes we're going to look into an analytical solution, but normally, no. We skip skip that part and go directly into the simulation, because in general our problems are going to be non-linear. Let's do some examples. Any questions? That's okay. We take an example from, well, it's going to appear on exercise 1. So what I'm about to do is the answer to exercise 1A or something like that. The problem, it's a classic, it's called Lotka-Volterra equations. From 1910, I think, so they are more than 100 years old. It is a biological problem. You are looking at an island. And on this island, you have a lot of rabbits. So R, that is the concentration, the number of rabbits on an island. And the number of rabbits is going to change with time. So the number of rabbits, that's a continuous function of time. We now say on this island, it's plenty of food. I don't care how many rabbits there's going to be there, it's food enough for everybody. But then, as you all should know, the rabbits, they are quite clever in making love, so they make a lot of babies. And we have the description, something like this. The change of the number of rabbits is proportional or goes like the number itself. Now that equation, if you stop there, is easily solved. You can actually solve it in your head. Then R of t equals some constant, say R0 exponential a times t. The constant a, just a parameter, just a number. So the number of rabbits, if you start here with R0, is going to grow exponentially. So that's just the rabbits. Then we introduce foxes. Now foxes, they like rabbits a lot. Rabbits, they don't like the foxes so much. So whenever a rabbit meets a fox, it's going to be negative. Constant b, and then the combination rabbit multiplied with foxes. That's negative for the rabbits, of course. For the foxes, well, left by themselves, they are in trouble. Because the foxes, they are not cannibals, and if they were, they're still going to be extinct. So the first term here is going to be negative. Parameter c times the concentration of foxes. So that one will be sort of the same solution. Okay, the foxes starts here, F0, but it's going to decay and in the end go all the way down to 0. So that's the solution for this problem alone. But when a fox meets a rabbit, then he gets some food, and then that's positive for the foxes. So parameter d, rabbit, and foxes. This is the equations. So as a prey and predator model, very simple. But the people studying biology, they peek into these kind of models. Of course, no diseases here, No food shortage for the rabbits, so it's a very simple model. What kind of set do we have here? Well, we have two dependent variables, R and F, rabbits and foxes. We have a system with two first-order ordinary differential equations. So yes, it's a second-order system, and it is nonlinear. This term here, they are nonlinear terms. So this one cannot be solved analytically. At least I can't do it. So skip that. We will do this one numerically. How do we do this one numerically? Well, a first order Euler numerical scheme, very simple. You do the following. You say a time derivative is almost the same as R new minus R old divided by some delta t. You make a discrete version of your equation, and then we just rewrite the equation here on the form R new equals R old, and then I say plus delta t multiplied with the expression for R dot. That will now be the right hand side of this equation. And then we start the program. This is all we need. Here you have a recipe. It's a first order method, very crude, very simple. So crude and simple, it should actually never be used. But it's so simple, this is the place you start. It's so easy, very easy. Regardless how complex this system is, how non-linear it might be, you can easily do this, no problem. That's right. So here we have Matlab. So now let us see if we can make a new script like this. And for a new script, yes? Yeah?
The error that is with the A, would it be old or errors?
Excellent question. So when we insert here the AR minus BR F, what should the R and what should the F be? Should it be the old one or should it be the new one? And here, always old. Always old. That is the first order Euler scheme. Explicit scheme, very easy to program. If you had the new one, then you are in trouble. Then you have unknowns here and here as well. Then you have to solve a matrix system. That's more tricky. So we always do the classical explicit first order Euler scheme. Explicit first order Euler scheme. This is the first thing you learn in a numerical course. So yeah, thank you. Other questions? Okay, let's do the programming here. I've fired up Matlab and have it now in the Matlab editor, and we always start with clear all. A very small script. Can you read it on the back there? Can you see it? Or is it possible to make the font bigger here? Shouldn't it be some view? No. It's okay.
Anyone knows how to increase the size in Matlab? Okay. Figure out for next time.
I'm going to put out this code on the homepage anyway as lecture examples, so don't worry too much about it. You can't read it. Just pay attention. Clear all. He will clear the memory. That's important in Matlab. If you have just run a program, you have done something stupid like pi equals 17. Now then he thinks pi is 17, which is a very bad idea if you want to use pi equals 3.14 or something. So clear all, it clears the memory. Second, close all. Destroys all old graphical figures. And any figure you want to use is popped in the foreground. If you don't use close all, then you have an old figure lying somewhere beneath all your windows and you don't see it. So close everything. Finally, CLC. CLC, that is a nice one. He will destroy this command window where you'll have a lot of red printouts. There you will find all the error messages when you do something stupid. But with the CLC, you clear this window. Then you know when you try to run and you get an error, it's only the latest error that is from the last run. So CLC always clears this command window. So you always start with those 3 sentences. That's all. Then we're going to need values for some parameters, and I found some numbers for them. Constant A is 1. Constant B is 0.002. C is 1/2. And D equals 0.001. The values for these are chosen so that the time scale is 1 year. So the time unit in my problem here is 1 year. And I want to simulate this for at least 20 years. So I have a maximum time, tmax of 20. We start there. Then I have a problem. For this numerical scheme, I have to choose a time step, delta t. According to theory, it should be small to have a good accuracy. But if it's too small, it's going to take 4 hours because Matlab is slow. So start with a fairly big one and then see how it goes. If you have time, use a smaller and smaller one until you see no change in the solution. Then it's small enough. So I start with 0.1. Then I need some initial values for this, for the rabbits. 1,000 rabbits and 100 foxes should be okay. Like that. Of course, here is a continuous model, but it's a little crude, isn't it? We are talking about real numbers here, so how does 0.5 rabbit look like? I don't really want to know. But we treat them as continuous functions, of course. I need a figure number 1. And then I need some graphical output when I do the time simulation here. So I write now hold on. Hold on, that means when you have created a figure, all graphical commands now following will go into the same figure. And you will remember all of them. So now we can do the time loop. For time t equals 0 with step delta t all the way up to t maximum. That's the main time loop now. So time t starts with 0 and then increase with delta t all the way up to 20 years. then we just write my new R's, new rabbits, equals the old ones, plus, that's not a plus, where is plus, that's a minus, where?
You have to switch
the
language of the key.
I found it. Plus, what should we have? We had delta t multiplied with, no, we don't have that either, where is multiplication? How do you find that one? Where's the star? Thank you.
There you go.
Yeah, it didn't help much. It's still Norwegian. Sorry. Beautiful. And inside here we now need small a multiplied with r minus b multiplied with r multiplied with f, like that. And then we have the same with the foxes. And for the foxes it was negative c times foxes plus d times rabbits times foxes, like that. Then we make a plot for the time, and then we make for the rabbits, they can be red circles, and then we have the foxes can be blue circles. Something like that. Let's see if it works. We try to run it. And we call it untitled. That's a beautiful name. And here we have the result. So we started out with 1,000 rabbits and 100 foxes, and the rabbits, they really love this, and they double their numbers, but the foxes comes after them, and then the too many foxes, and then the rabbits go down, and now you'll have this oscillating behavior every 11th year or something with this model. And this simulation here is wrong. It's not correct. So where is the adult? Where did I go wrong? Of course, it's not accurate because I have a delta t, which is a little big, but well, it looks okay, doesn't it? Anybody see the adult? Something to do with the question we got here. What about these guys? Should they be old or new? Well, according to the Euler scheme, everything on the right-hand side should be old. So here we have old R and F's, old rabbits and old foxes. For the first sentence here, that's okay. But here I overwrite the value. So for the second equation here, for the concentration of foxes, he uses the R here. Well, that has just been updated. That's not good. I should have the old R here. So I have to actually make a reprogramming. Just to be certain, you can do it like this. New rabbits and new foxes. And then you make rabbits equals new rabbits foxes equals new foxes. Now it is explicit first order Euler scheme, which for this example was actually a bad idea. Strangely enough, he is quite inaccurate. It was more correct with the adult, because here you see the peak is going to increase. If I had continued above 20 years, going to 200 years, this is going to explode, and that's not correct. It should be the same level. So it was actually a better numerical scheme with the adult, but how did we know? So forget about that. We just decrease the delta t, 0.01. And now the computer has to work a little bit longer, but there you see fairly okay results. Not precise, but fairly precise. So this is how you can easily make a program with first order Euler scheme. So in exercise 1 you will be given the same problem, and then you have to continue with this problem here. We are also then going to include hunters. And hunters, as you know, they will shoot at anything that moves, including other hunters. So that can be a little bit tricky. But also we will introduce a nasty little problem there with time delay. Because the hunters, they are not so bright, sitting on the pub drinking beers. Then they hear a rumor, now there's plenty of rabbits out in the forest. But that information might be 2 or 3 weeks old. So then what's going to happen? You have a different time delay there. So that's a challenge you are going to get for the first exercise. Now, we won't have any guidance for the first exercise on this Friday. It will be next week. So we'll continue on Tuesday next week, 18 to 20, wasn't it? I'll see if I can get a bigger room. This one was a little bit crowded. Any questions? Then we stop here.